Hey, this is chapter 33. As you see, it's about surface roughness and its measurement. You're only responsible for this part of this chapter. You're not responsible for friction, wear, and other lubrication, but in different chapter, we will be going back to this last subsection. But right now, I'm not going to cover this last section. I will be only discussing the second and the third subsections. So why surface structures are important? Surface roughness is important since manufacturing of the parts actually depends on the surface quality you want to have at the end of this manufacturing processes. Depending on the requirements of the customers, other people, you can select different manufacturing processes and try to produce the part in a shorter time or in a longer time with higher surface qualities. If you want to have a higher surface quality, then that means surface roughness values should be as low as possible. And let's have a look at first the surface structure and its integrity. Here you see a schematic showing a typical metal, and this metal is divided into some sections. We have the metal substrate here. Underneath you see we have larger grains, and then we have work hardened layer. In this part, we need to have some plastical deformation, otherwise you cannot have such work hardening. Work hardening only happens once you have plastical deformation on the metal, and this may happen with some various operations. And if you have it with the help of sliding against tools or dies, then probably we are going to have some thicker work hardened layers. This is a work hardened layer. The thickness depends on the type of plastic deformation actually you are employing on the metal. Then we have amorphous layer, as you see here. For the amorphous layer to be obtained, you need to actually have some high heat employed, or even you may need to melt your metal. And the thing is that after this melting, your part should be cooled as soon as possible. Otherwise, you will have time, the metal will have time to develop larger grains, but if it is cooled rapidly, then we will have smaller grains, and we will have a kind of a crystalline structure. Then on top of this amorphous layer, we have the oxide layer, and the metals actually have different oxides depending on the type of metal you are working with. For instance, with an iron, then we will have iron oxide on top of the surface. If it's an aluminum, then we will have aluminum oxide. For copper, we will have copper oxides. And these oxide layers usually have higher hardness values than the below parts. Their hardnesses are much higher. And due to these high hardness values, they are more abrasive and they can withstand to higher impact forces. And then we have, after the oxide layer, we have some absorbed gases or moisture, and that's a very little layer. Its thickness is not too much, as you see. It's about 1 nanometer. And after the absorbed gas moisture layer, we have the contaminants, and its thickness is a bit higher compared to the below one. And in this final layer, we usually have dirt, dust, some other lubricant residues. And if the part is, and if you are going to use this metal for critical applications, then it's better you eliminate oxide layer, absorbed gas, and contaminant layers. What about surface integrity? It's actually describing not only the topological features, but it's also about the physical, chemical properties, their metallurgical effects. So it's some kind of a broad term for the quality of the surface. And its important sense, it affects the fatigue strength of your part, its resistance to corrosion, its service life, its overall strength, all depends on the overall surface integrity. So if you are going to use your part in a very critical aerospace application, let's say, then you should check all the details about your surface. And on the surface, we may have some defects. What are the type of defects? We may have some cracks on the surfaces, sometimes internal or external. We may have some craters on the surface. We may have heat affected zones, inclusions of various materials, elements inside, intergrain attacks between grains inside. So there are such defects, as you see. There are many of them. And if you want to improve the surface integrity, if you want to improve the quality of your part, then you should eliminate these surface defects as much as possible. Now let's have a look at surface texture and roughness in general, and try to focus on the measurement of surface roughness. And as you see, this is a typical surface texture, and we can define a surface profile in terms of 3 geometric attributes. The first one is area form. Although we want our surface to be horizontal, as you see, it is an area form and it's going upwards to the right. We don't want to have any waviness, but as you see, this is the actual surface profile. We have a kind of an waviness on the surface, and furthermore, we have the roughness. And the roughness is about these little peaks and valleys on the profile, and we can do some measurements on this roughness, and we will see in a moment how it is measured. And if you want to tell more information about the surface quality, then you should tell the form of this area, the waviness, the width of the waviness, and the lay directions, roughness spacing, roughness height. So these are all important parameters, variables, while defining the surface texture. And the surface texture obviously depends on the type of defects you have on the surface, scratches, cracks, holes, craters. They all affect the quality of your surface texture. The lays is the directionality, the direction of our predominant surface pattern. And if you look at here, we have lays in this direction. Then we discussed the roughness. It's the irregular deviation in small scale, not in a larger manner, but in small scale. And we'll be focusing on the measurement of this roughness. But here, the height and the width of these deviations are important. And the last one is waviness. I talk about it. The surface profile, the overall surface waviness affects the surface texture. Now let's focus on how we measure the surface roughness. This is a typical image of a surface, as you see. And what we do, we take some measurements at these instances. And as you see, we have equal intervals between these measurements, A, B, C, D, and other measurements below. So the first thing is that after you get these measurements, you need to draw a line, a datum line, at the center, so that the area of the below regions, the sum of the areas of the below regions should be equal to the sum of the areas above this datum line AB. Okay, this is the first thing we need to do after we get the measurements with equal intervals. And then we can simply determine the arithmetic mean value, RA, surface roughness. This is the most popular one. We mostly use RA value while defining the surface roughness, but rarely, depending on specific cases, we may also use root mean square or RMS roughness value. Let's have a look at the first one. It's not complicated. After you got these values, then what we do, we simply sum them together and divide with the number of measurements, and they should be absolute values. Okay, this is, you cannot have negative values here. They are all positive. We are making use of absolute values. And let me remind it once again, the datum line AB is located such that the sum of the areas above the line is equal to the sum of the areas below this line. It's an important issue, and we make use of it also in the root mean square roughness calculation. The only difference is that this time we are taking the squares of the measurements and then taking the mean of them, and lastly taking the square root of these summation and division operations. And this will give us the root mean square roughness value. And I will put the link of this video. Please have a look at how they calculate the surface roughness values. You can find the link below. And let me briefly talk about whether these measurements are enough or not. Since, as you see, if you take such measurements, these are not alone enough to define the overall texture of a surface. You may have a little crack and your measurement may not be going into that crack. And if that's the case, then you cannot just say that RA value is enough to describe the behavior of your surface. If you want to actually go into details of your surface quality, then you should also perform other measurements, use another microscope, maybe take 3D measurements, and then later comment on the quality of your surface. For the measurements, for 1D measurements, we make use of surface profilometers. I will record another video on this case. Since I have a simple surface profilometer, I will measure some typical parts and show you the results. And here is an example. This is the head of an surface profilometer. At the tip of this head, we have a stylus. This is a diamond stylus, and its diameter is very low, around some micrometers. What actually this surface profilometer is doing is that it moves over the surface, goes into these volleys, goes over the peaks, and then during this movement, it takes some measurements as we discussed here. So it gets these measurements, and then its little computer inside performs some computations and give you the resulting surface roughness value in terms of mostly RA, or if you change it, it can even give you RQ value, RMS value of your surface. And the diameter of the tool is quite important. It's better you use small diameter if possible. If you look at here, for instance, even though we have such deep volleys, our stools cannot go into the deeper of this surface since the diameter is larger, and that's why we have difference between the actual surface and the pad of our stylus. So we cannot say that the resulting RA value is exactly the surface roughness value of our surface. It's just a kind of an approximation. In this figure, you can see some typical profiles after different manufacturing operations. Here you see some high quality grinding or finishing operations. Lapping is one of them. As you see, the distance between the volley and the peak is 0.5 millimeter. If it's a finished grinding operation, it's a bit higher. But if it's a rough grinding operation, then you see that it's much higher than the previous two. And it's again similar in turning operation. It's a very conventional machining operation. And again, we have higher volley to peak values. And as I said, if you're not satisfied with the 1D measurement, then you may try to have 3D measurements, three-dimensional surface measurement. For that purpose, we can make use of some optical interference microscope or atomic force microscopes. With the help of them, you can get such images and you'll have more information about your surface quality. But obviously, these are much more expensive than the 1D surface profilometers. And here you see some typical surface roughness values of different mechanical products. For instance, the balls and the bearings have higher surface quality. Their surface roughness values are usually around 25 nanometers. But if you look at some, let's say, disk faces, clutch disk faces, it's usually around 3.2 micrometer. Again, we have low values for the bearings, but higher values for some typical mechanical products. And this is all for this chapter. And as I mentioned, I will be recording another video for typical measurements of different products. Thanks for watching. Please have a look at the below video.